Hello everyone, welcome to lesson 6. This is the definition of the derivative, and in these videos we're going to talk about average rate of change, instantaneous rate of change, and I'm going to introduce you to the two definition of the derivatives that you need to know for this class. So the first thing we want to understand about the definition of the derivative, how we want to introduce it, is that we have a curve, and we're going to choose two random points on that curve, and we're going to draw a line through those 2 points. And so when we draw a line through these points, we've created ourselves what we call a secant line, right? So this is our secant line. The secant line, just like in geometry, right, we have a circle and we have a line that connects through 2 points. We also call this a secant line. So that's where you've actually heard that word before. And so what I want to understand is I want to know what the rate of change is, or the average rate of change of the function between these 2 points. So I want to know what the average rate of change is between the point A and the point B. Well, this is actually going to be equivalent to the slope of the line that's connecting these 2 points. So essentially, this is going to be the slope of the secant line. And so we already know that I'm going to go ahead and I've created this really not so great coordinate plane here with a y-axis and an x-axis. And so this is point A and this is point B. So our corresponding y value would be f of A, and our corresponding y value for B would be f of B. So if I want to find the slope of this line, you guys already know that slope is just going to be the change in y with respect to the change in x. All right, so this is going to be the slope of our secant line. And this is also going to be what we're going to consider the average rate of change. Now we're going to get more specific into what this means later in the course and like what it actually represents. But for right now, all I want you guys to interpret average rate of changes is you're finding the slope of 2 points. All right, so it's very straightforward, pretty easy to do. So when you see average rate of change, and by the way, I just wrote it right here, but average rate of change, we're really good about abbreviating this as AROC. So you'll see AROC a lot of times in my notes, and that just means it's the average rate of change. But one thing, and I'm getting ahead of myself here, please don't confuse average rate of change with average value. When I do the video on average value, I will go back and just reiterate it's not the same thing as the average rate of change. So let's look at these two examples. Very straightforward. So it's given the function y equals x squared minus 3. Find the average rate of change, right? Average rate of change of y over the interval from 2 to 3. So you guessed it, ladies and gentlemen, the average rate of change is just going to be the slope of this function on the interval from 2 to 3. So it's going to be f of 3 minus f of 2 all over 3 minus 2. And you want to make sure that you show work for some of these questions. If it's multiple choice, you don't really have to, but for FRQs, you want to be able, you get a point for showing, usually you get a point for showing this formula right here. So over here to the side, we're going to look at what is f of 3, or actually let's do this. Let's say instead of y, let's go ahead and write f of 3, right? So f of 3 is going to be equal to, and we're going to plug in 3 here, we're going to get 3 squared, which is going to be 9. 9 minus 3 is going to be equal to 6. And we're going to go ahead and do f of 2. F of 2 is going to be 2 squared, which is 4. 4 minus 3 is going to be equal to 1. So we just plug and chug. We're going to get 6 minus 1 all over 3 minus 2 is 1. And so we get that the average rate of change here is going to be 5, right? 5. So pretty straightforward, I hope, with these questions. And we get more into the meaning of what average rate of change is later in life. Today I'm going to keep it very light with you guys, and we're just going to do just basic stuff. So I'm going to ask you guys, given the function f of x equals the natural log of x minus 2, we want to find the average rate of change over the interval from 1 to e. So just like before, we're going to find the slope of f of e minus f of 1 all over e minus 1. And yes, if you did f of 1 minus f of e over 1 minus e, it would all work out in the end. The signs would be the same at the end. So, you know, but I always just go right to left. I always like to do f of e minus f of a, but it doesn't really essentially matter. So we're left with the natural log of e minus 2. Well, hopefully you guys know what the natural log of e is. That is 1. 1 minus 2 is equal to negative 1. So I know that f of e is negative 1. And then I'm going to do minus, and then this is going to be f of 1. F of 1 is going to be the natural log of 1 minus 2, where the natural log of 1 is 0. 0 minus 2 is negative 2, so it's going to be minus a negative 2 all over e minus 1. And so we're left with, up here, we're left with plus, right? Minus a negative is plus a positive. So it's going to be 2 minus 1, which is going to be 1, all over e minus 1. And this is going to be your average rate of change for this problem. All right? So, average rate of change, slope. You are going to be given an interval and you will be given a function. So, there should be no reason why we can't do average rate of change, right? Pretty straightforward with this. So, now we've talked about the equation for slope of a secant line. So, let's talk about the slope of the tangent line. So, there's going to be a diagram given to you guys here in a second, but the tangent line is actually really important. I'm going to go back to our good old friend geometry for a second. And if we were to draw a line on a circle at one point, we call this again the tangent line. Well, very similarly, if we go and look at a curve, and again, there's going to be a much nicer picture on the next slide for you guys here. But I got myself 2 points. And again, if I were to connect these 2 points, then I would have a secant line. But what we really want to do is we're going to call this A, we're going to call this B, and the distance in between these two things is going to be our delta x, right? Our change in x. What essentially we want to do is we want to actually make delta x get really close to 0. All right, and we're going to talk about this in a second. Once we do that, then our function, our points, are actually going to get closer and closer together to the point where delta x actually becomes 0. And when that happens, we actually create ourselves a tangent line at some value. Well, that's what so at this particular value, we call this the instantaneous rate of change. All right, so this is what's happening right at the actual value. So this is going to be the derivative of our function, and more specifically, and again, we'll get to this much more, it's going to be the derivative at some value a. So average rate of change, we give you an interval. For instantaneous rate of change, we want to know exactly at a value. So we say x is equal to 3 is our example. So let me show you guys what I just did on the next page. Okay, so now you guys can see what we're talking about here in these nice little visuals. So we start out with a curve and we have 2 points and we created a line through those 2 points. And again, this line right here is called the secant line. And again, the slope of this line is going to be the average rate of change from P to Q on this curve that's right here. So what we want to do is, again, the distance between these 2 points is going to be delta x. And we want to go ahead and start making delta x get smaller. We want to get smaller and smaller to the point where delta x is actually going to be equal to 0. So the closer and closer these points become, the secant line then starts transforming into an actual tangent line. And so if I want to know what's happening in f prime of p, right? So what is the instantaneous rate of change at this point P? I want to find the equation, the slope of this line right here. So what we're going to do is going to actually create the definition of the derivative based on that. So this is a kind of the example of what's written for you guys here. I went ahead because of, I know my confusion of my students. So I went ahead and redrew our little picture that you guys see right here. And so what this says is that we have a slope of a secant line through the point P, which is f of x. So here's x, and then the corresponding value would be f of x, right? If this is 3, this would be f of 3, so that we get here. And then some delta x difference, so we've now moved over a delta x. This distance from the origin, here's x, plus this distance here, which is delta x, gives you our new value, x plus delta x, which is this value of x, and then again, our corresponding y value would be x plus delta x. And so what we're going to do is we want to find the equation of the secant line. We want the equation of the line that goes through these 2 points. We're using slope. Again, we're going to do the change in y first. So we're going to go f of x plus delta x minus f of x. So this is going to be q minus p. And then I'm going to then take the change in x, which is going to be x plus delta x. That's our q x. And then we're going to subtract x like so. So this is going to be the idea of what we're going to do. So now we found the equation of our secant line, right? The equation of our secant line that looks like this because our x is canceled on the bottom. But we don't want the equation of the secant line. We want to get where these 2 points get closer and closer together to where they come one single point, so we can create ourselves the tangent line. So again, the distance between these 2 points is delta x. Well, we want delta x to actually get very close to 0. So what we're going to do here to find our equation of our delta x is we're going to take our slope of our secant line and we're going to add the limit, and we want delta x to approach 0. And now we've changed the equation of our secant line to the actual equation of our tangent line. We're actually finding the definition of the derivative. So this is the very first one that we did. Okay, so what we're going to do in the next video is actually apply these two theorems. So I've showed you guys one of them, and I'll do the other one as well. This one's the general equation for it. This is the general equation where we're not sure what value we're looking at. And then the other one is what if we know where x approaches, if it's actually approaching a value that's not 0. So in the second video, we're going to actually do some examples of the definition of the derivative. So I'll see you guys in part 2.